10th standard geometry, circles. Circular figures are a part of our daily life. For example, a wheel, a chapati, a ring, a pizza, a dartboard, a clock are all examples of circle. We have studied in previous class that a circle is a collection of all points in a plane which are at a constant distance called radius from a fixed point center. All of these points are equidistant from the center. Collection of all these points form a circle. Circles passing through 1, 2 or 3 points. Circle passing through 1 point. Point A. How many circles can pass through this point A? One circle can pass through point A, 2 circles or 3 circles can pass through point A. How many more circles can pass through point A? Infinite circles can pass through 1 point, particularly in this case A. Circles passing through 2 points. We have 2 points A and B. We can draw one circle that can pass through both the points A and B. 2 circles that can pass through both the points A and B. 3 circles that can pass through both the points A and B. How many more circles can pass through point A and B? Infinite circles can pass through 2 distant points. Circles passing through 3 non-collinear points. We have 3 non-collinear points A, B and C. To find out how much circles can pass through the point A, B and C, let us do a construction. Join segment AB and BC. Bisect both the segment AB and BC. We know one property, that every point on the perpendicular bisector of a line segment is equidistant always from its endpoint. So, if we keep O as a center, OA will be equal to OB and OB will be equal to OC. Hence, OA equal to OB equal to OC. So, keeping O as a center and OA as a radius, the circle will pass through all the 3 points. There is a unique circle passing through 3 non-collinear points. Circles passing through 3 collinear points. Consider 3 points P, Q and R which are collinear. P, Q and R, collinear points, and they lie in a straight line. If we try to draw a circle in the following manner, we know that one point R will lie outside the circle. Or if we try to draw a circle in this manner, we know that one point, particularly Q, will lie inside the circle. It can be seen that if 3 points are collinear, any one of the point may lie outside the circle or inside it. Therefore, a circle passing through 3 points where the points are collinear is not possible. Recall. Infinite circles pass through 1 point. Infinite circles pass through 2 distant points. There is a unique circle passing through 3 non-collinear points. No circles can pass through three collinear points. Let us now examine the different situations that can arise when a circle and a line are given in a plane. Case 1. In this figure, Case 1. In this figure, the line PQ and the circle have no common point. In this case, PQ is called a non-intersecting line with respect to the circle. Case 2. In this figure, there are two common points A and B that the line PQ and the circle have. In this case, we call this line PQ a secant of the circle. Case 3. In this figure, there is only one point A which is common to line PQ and the circle. In this case, the line is called tangent to the circle. Definition of tangent. The tangent line to a plane curve at a given point is a straight line that just touches the curve at that point. Given a circle, a line that intersects the circle at point A is called as a tangent to the circle. Number of tangents from a point on a circle. Case 1. A point lying inside the circle. Point P lies inside the circle. If we try drawing tangent line passing through point P, those tangent line will intersect the circle at 2 points. Hence, there is no tangent to a circle passing through a point lying inside the circle. Case 2. A point lying on the circle. In this case, point P lies on the circle. If we try drawing more than one tangent line, that line will intersect the circle in two distant points. Hence, it will no longer be a tangent. Therefore, there is one and only one tangent to a circle passing through a point lying on the circle. Case 3. A point lying outside the circle. Point P lies outside the circle. There are exactly two tangents T1 and T2 to a circle through a point lying outside a circle. Tangent theorem. Theorem. A tangent at any point of a circle is perpendicular to the radius at the point of contact. Given line L is a tangent to the circle with center O at the point of contact A. To prove line L is perpendicular to radius OA. Proof. Assume that line L is not perpendicular to segment OA. Suppose segment OB is drawn perpendicular to line L. Of course, B is not same as A. Now, take point C on line L such that B is between A and C and BA is equal to BC. Now, in triangle OBC and triangle OBA, segment BC is congruent to segment BA by a construction. Angle OBC is congruent to angle OBA as each of them are right angle. Segment OB is congruent to segment OB as it is a common side in both the triangle. Therefore, triangle OBC is congruent to triangle OBA by SAS test. Therefore, OC is equal to OA. But OA is a radius. Therefore, segment OC must also be the radius. Therefore, point C will lie on the circle. That means line L intersects the circle in two distant points A and C. But line L is a tangent, and that is given to us in the statement. Therefore, it intersects the circle in only one point. Our assumption that line L is not perpendicular to radius OA is wrong. Therefore, line L is perpendicular to radius OA. Converse of tangent theorem. A line perpendicular to a radius at its point on the circle is a tangent to the circle. Given M is the center of a circle, Mn is a radius, line L is perpendicular to segment Mn at N. To prove line L is a tangent to the circle. Proof: take any point P other than N on line L. Draw segment MP. Now, in triangle MNP, angle N is a right angle. Therefore, segment MP is a hypotenuse as it is opposite to the right angle. Therefore, segment MP will be greater than segment MN. As segment MN is a radius, point P can't be on the circle. Therefore, no other point except point N of line L is on the circle. Therefore, line L intersects the circle in only one point N. Therefore, line L is a tangent to the circle. Recall the two theorems. Tangent theorem. A tangent at any point of a circle is perpendicular to the radius at the point of contact. Converse of tangent theorem. A line perpendicular to a radius at its point on the circle is a tangent to the circle. Tangent segment theorem. Tangent segments drawn from an external point to a circle are congruent. Given point A is the center of the circle, D is a point in the exterior of the circle, points P and Q are the points of contact of the two tangents from D to the circle. To prove segment DP is congruent to segment DQ. Construction. Draw radius AP and AQ. Proof. In triangle PAD and triangle QAD, segment PA is congruent to segment QA as they are the radius of the same circle. Segment AD is congruent to segment AD as it is a common side in both the triangles. Angle APD is equal to angle AQD is equal to 90 degree by tangent theorem. Therefore, triangle PAD is congruent to triangle QAD by hypotenuse side test. Therefore, segment DP is congruent to segment DQ by corresponding sides of congruent triangles. Practice set 3.1, sum number 1. In the adjoining figure, the radius of a circle with center C is 6 cm. Line AB is tangent at A. Answer the following questions. What is the measure of angle CAB and Y? Second, what is the distance of point C from line AB and Y? Third, distance AB is equal to 6 cm. Find distance BC. Fourth, what is the measure of angle ABC and Y? Solution. It is given that line AB is tangent to the circle at A. Therefore, angle CAB is equal to 90 degree by tangent theorem. The theorem states tangent at any point of a circle is perpendicular to the radius through the point of contact. Thus, the measure of angle CAB is 90 degree. Distance of point C from AB is equal to 6 centimeters as it is the radius of the circle. Third, triangle ABC is a right angle triangle. CA is 6 centimeters and AB is equal to 6 centimeters. By using Pythagoras theorem, we have BC square is equal to AB square plus CA square. Therefore, AB is 6 and CA is also 6. By substituting and simplifying, we get BC equal to 6 root 2 centimeters. Thus, distance BC is equal to 6 root 2 centimeters. Practice set 3.1. Sum number 2. In the adjoining figure, O is the center of the circle. From point R, segment RM and segment RN are tangent segments touching the circle at M and N. If OR is equal to 10 centimeters and radius of the circle is equal to 5 centimeters, then first, what is the length of each tangent segment? Second, what is the measure of angle MRO? Third, what is the measure of angle MRN? Solution. It is given that segment RM and segment RN are tangent segments touching the circle at M and N respectively. Therefore, angle OMR is equal to angle ONR is equal to 90 degree by tangent theorem, as tangent at any point of a circle is perpendicular to the radius through the point of contact. Therefore, OM is equal to 5 centimeters and OR is equal to 10 centimeters given in the question. In triangle OMR, by using Pythagoras theorem, OR square is equal to OM square plus MR square. By simplifying this and substituting OR as 10 and OM as 5, we get MR to be equal to 5 root 3 centimeters. Tangent segments drawn from an external point to a circle are congruent. Therefore, MR equal to NR is equal to 5 root 3 centimeters. In triangle OMR, tan of angle MRO is equal to OM upon MR. As we know, tan theta is equal to opposite upon adjacent. So for angle R, OM is the opposite side and MR is the adjacent side. Therefore, OM is 5 centimeters, MR is 5 root 3 centimeters. 5 will get cancelled from the numerator and the denominator. Therefore, tan of angle MRO is equal to 1 upon root 3. We know that tan 30 is equal to 1 upon root 3. Therefore, angle MRO is equal to 30 degree. Similarly, angle NRO is equal to 30 degree. Fourth, angle MR is equal to angle MRO plus angle NRO, which is equal to 30 degree plus 30 degree, which will be 60 degree. Thus, the measure of angle MRN is 60 degree. Next, in right angle triangle ABC, AB is equal to CA is equal to 6 centimeters. Therefore, angle ACB is equal to angle ABC, as equal sides have equal angles opposite to them. Also, angle ACB plus angle ABC plus angle CAB is equal to 180 degree by using angle sum property of triangle. Therefore, angle ABC plus angle ABC plus angle CAB is equal to 180 degree. We substitute ABC in place of ACB, as ACB is equal to ABC. By adding it, we get 2 angle ABC plus angle CAB plus 1 is equal to 180 degree. We know that angle CAB is 90 degree. Therefore, by substituting 90 degree in place of CAB, we get 2 angle ABC plus 90 degree is equal to 180 degree. By taking the plus 90 degree on the other side, we get 2 angle ABC is equal to 90 degree, and by taking the 2 on the other side and dividing it by 90, we get angle ABC is equal to 45 degree. Thus, the measure of angle ABC is 45 degree. Practice set 3.1, third sum. Segment Rn and segment Rn are tangent segments to a circle with center O. Prove that segment OR bisects angle MRN as well as angle MON. Solution. In triangle OMR and triangle ONR, segment MR is equal to segment NR, as tangent segments drawn from an external point to a circle are congruent. Segment OM is equal to segment ON, as they are the radius of the same circle. Segment OR is equal to segment OR, as it is a common side in both the triangle. Therefore, triangle OMR is congruent to triangle ONR by SSS congruency criteria. This implies angle ORN is equal to angle ORN, as they are the corresponding parts of congruent triangles. Also, angle MOR is equal to angle NOR by the similar reason, as they are the corresponding parts of congruent triangles. Therefore, segment OR bisects MRN and angle MON. Let us recall. First, a tangent at any point of a circle is perpendicular to the radius at the point of contact. Second, a line perpendicular to a radius at its point on the circle is a tangent to the circle. Third, tangent segments drawn from an external point to a circle are congruent.